For the sake of the recording, this is the data facing call for June. We're trying out an unconference session where we have proposed some topics that the group wants to discuss, and they will just spend the session discussing those. And the discussion topics we've chosen are data workflows after the death of unlimited cloud storage, and data workflows for data in the terabyte or greater range. All right, so the one with the most votes was the terabyte or greater, so let's start there. So I actually proposed this one. This is something I was dealing with at the University of Michigan before I left. Life sciences is getting into microscopes that produce terabytes a day, which is a lot. And particularly, I'm thinking of it from like a microscopy core perspective, because that's where these instruments are likely to be available. So a terabyte quickly eats up the local storage on whatever computer is controlling the actual instrument. So how do you actually do data delivery and access on shared instruments like this? Previous workflows definitely relied on local storage. So what other issues are people seeing with things in like terabytes?
What other use cases?
Mm-hmm.
Telescopes,
Mm-hmm.
particularly
Oh,
the new,
telescopes.
yeah, the new large aperture ones that are coming online, South America.
Okay, so other magnification direction.
Mhm.
And then there are hyperspectral imagers, which is where we're starting to see a lot of growth. Not
And
terabytes a day, though.
so I can say in industry, we're not ingesting that much data. However, we have now stored roughly a petabyte of data on-prem. We're using a GPFS system from IBM, which, well, that's what it's built on anyway. There's some other functionality.
Yeah, I know of, so I can talk to some strategies that I know have been used for the microscopy case. Other use cases I know of are where folks are doing like really large simulations of a variety of different types of particles. So it could be like simulate like astronomy simulations, simulations of stars or whole galaxies, or simulations of large biomolecules, sometimes surrounded by like aqueous solution, where there are, millions of atoms in a single simulation. And then a variety of other types of kind of physics-based simulations that are applied to anywhere from biology to chemistry, physics, astronomy, et cetera, engineering, like air particles through a cow barn. Um, and those produce a lot of data, not necessarily at the same rate as the microscopes, but they tend to sort of accumulate over the course of the simulation, and then they need to be processed. They need to be like distances calculated and rates of change and thermodynamics sometimes. And so that data has to be moved to where it can be at least, reduced or represented in different ways for all those analyses. Yeah, weather simulations, very, very much in the same kind of boat there, as somebody else pointed to. Frequently, those are like produced on a large computing system, which might be at the campus or might be a national system, but then it has to be like brought down somewhere where a graduate student can be analyzing it and making figures eventually.
Yeah. Which, to that point, I will say I don't keep up with this specific domain, but I do know as of a few years ago, NOAA claimed to have one of the world's largest data sets. Apparently, one of the conferences I went to, they claimed that it was so large that it was more effective for them to literally ship an array of hard drives rather than try to transfer it. So if you ever were awarded a research grant or something where you got access to the data, that's how they would provide access. It's just ship you this big, I don't know, it was somehow packed in a safe way of it.
Yeah.
But I think there
Yeah.
is some good case studies. If anyone wants to look, I think you could probably find some good case studies to review.
Yeah, that's definitely an interesting one. So, and Jim, for these telescopes, how is data collection currently done?
Well, so it's interesting. Looks like I broke up there for a minute. It is interesting because it has to come down off a mountain, so it's usually if via fiber from the mountaintop, and a lot of the discs at the top have to be pressurized because there's a serious difference in pressure when you go from where the ground station is to where the telescope is located on some of these mountains. Which a lot of people don't think about. And so you have to have, and then I know the Vera Rubin one it has fibers, dedicated fibers that go to Fermilab, I believe, for, in Chicago for all that data. And then the data is deposited from there. And some of there's a Mexican telescope, Hawk, which is it's a Cherenkov detector, so it detects high energy particles. So it's particle astronomy rather than light astronomy. And that too has to have similar provisions for, a high speed fiber net too, somewhere in the United States. And I think that one goes into the University of Miami. I could be wrong on that one. So it has to be, when you decide to build a facility at that scale, you have to come up with a really good data management plan and a way to get it from where these highly capable sensors to where it can be analyzed, stored, and analyzed.
Have you heard if they're using the Globus framework at all? If you're familiar with that?
I believe they are. Yeah.
Okay.
Yeah. So. That's what I was going to say too, is that almost all of this, Globus is one of the best solutions for moving things around. And I was trying to see, we were negotiating, when I left Penn State, we were negotiating a Net Plus agreement but I don't see that on the Internet to Net Plus site. Do you know anything about that, Lauren? Yeah.
I know a little bit about Net Plus in general, but
Yeah.
Net Plus is really like, my understanding, the suite of different contracts that Internet2 has negotiated with different vendors. And some of those prices, most of those prices are available to anybody, even if your campus is not an Internet2 member, and just a few of them have like exclusive pricing or pre-negotiated contracts for academic institutions with only if you're an Internet2 member.
Right.
Yeah, I'm Jan Day with AWS. I can speak to the Internet2 Net Plus program in some detail. I manage our relationship with Internet2, specifically the Net Plus AWS program. And yes, it's about the program as a whole is about 22 to 25 solutions that Net Plus and the higher education community has pre-negotiated with those vendors to offer contracting that uses terms that higher education needs to see, right? BAAs, FERPA, HIPAA, those kinds of things are included in the pre-negotiated contract, and then very nice discount negotiated because of just numbers being able to commit to that. But what my most favorite part of the Net Plus program is the communities of practice that form around each of those solutions. So Whether you're using Kion or Blackboard or DocuSign or ServiceNow or AWS or Google, they each have a really engaged community of practice that helps institutions, not have to reinvent the wheel. So recommend.
Cool. I want to go back to a comment Lauren put in. She was mentioning that sometimes you have to focus on data reduction, meaning like you need to figure out a new data structure, or you need to do some on-site processing, like streaming or something, before you even put it to disk. And that's just something that's been in my mind for a lot of things too, especially like with imaging. Like it's still like literal image files. It's just really large ones or a lot of them. And my first kind of intro to programming was MATLAB. So I always think about their sparse matrix data structure. I'm like, it just makes a lot of sense to me, because like in a lot of images, it's not a lot of detail. You're usually just like finding like maybe a cell and tracking it when it moves or something. It's like there's got to be a better way to actually store that data that's more efficient. So I'm not like a specialist in anything. I know a little bit about a lot of things for my job. Is there anyone who knows how like streaming type of things are actually done? Always wondered about that.
Well, one of the ways I know, so we had several different types of microscopes at UW-Madison in a building, and they were literally placed in the room next to the large data center that had lots of storage. And so they were sent immediately from the instrument. And I think there was some pre-processing stuff that happens mainly on the computer that controls the microscope. So there was even some reduction happening there. But it was getting saved directly to drives that were then, in the same room with computing hardware. And then they had like a workflow that they would trigger that would do some reduction, so that then the reduced stuff could go to different laptops or computers or whatnot, and to other computing systems. But that way, like the really large data was saved in its sort of semi-permanent place, right there in the next room. And like even the reduction that I mentioned in what the National Radio Astronomy Observatories do is that there's a lot of like data reduction that happens at the satellite. And then for the arrays that are within a smaller geographic region, they have huge data centers that are all about just reduction, or sort of like pulling out different features from that raw data so that it can be made available to scientists elsewhere.
And one thing I'll say as far as streaming data, it becomes a bit of a misnomer, because if you really start diving down into some of the computer science of it, I mean, everything down at the bit level becomes chunked at some point. So some of the first questions when you start talking about streaming data is, what's the refresh rate? I mean, even, I work at Caterpillar, but I also collaborate a lot with Iowa State. Anyway, even some of our applications where we claim the data to be streaming, in reality, it's being batched somehow. It might be batches, maybe a few batches a day, or some of our applications are actually getting down. In a few instances, I have seen something like 10 hertz, but that's pretty rare. And even in those cases, I do know some of those applications are still yeah, the data, some of that data might be 10 hertz, but even some of that, if you start looking through the data pipeline, is still being somehow streamed, but with batches behind it. So it's not truly like end-to-end streaming. From my experience, I mean, I do know that there are examples out there, but there seems to be very few examples that are truly streaming data from your whatever edge device you might be working with to your final application. One thing I have seen, IBM with their I think what used to be called I think it was, oh geez, what was it now? Prophecy. The Prophecy platform used to have some streaming capabilities that we made use of. But again, it was a struggle to actually establish that data pipeline and to keep well, all the devices along your pipeline, keep them online and available, and actually keep them robustly generating data is a very big challenge. Even right now, actually, we have another team in my division that is looking at doing some federated learning using edge devices, and they're attempting to stream it, but right now they're still using batches of data where we're storing data on hard drives. There's an ECM on board, and we're collecting that data in batches again.
So I work with the LIGO team. It's the Gravitational Wave Observatory, and they do real-time signal processing from the two LIGO arrays. The streams get combined, and they do some real-time stream processing, and it is buffered like you said, but it's nearly real time because it has to be, because once they get a detection, they put a, or something that they suspected as a detection, they try to localize it and then call out to observatories that are within that window of the sky that maybe can see what the optical component or the radio component or the X-ray component is of the, because usually it's like two black holes colliding or a black hole and a neutron star. So it's travels at the speed of light. Gravity travels at the speed of light, and we need to basically see what happens before it actually lights up in the visible light or in the X-ray signal. So yeah, we used Apache Kafka for that. That was some of the which is a free thing. It's under the Apache license, and that seemed to be really useful in the real-time streaming world. That was a huge project. And then, Lauren will be happy to know that we used the Condor system on the way to do the individual, chunk the signals up and do the individual signal processing on that.
So what kind of data integrity is LIGO looking for? Like, right, thinking about streaming data, like, it's very possible that some is just dropped because there's a hiccup in the speed of all the parts. Is that like compensated for, or do they just deal with it and let it drop, or?
Yeah, sort of the way they deal with it is that they have two LIGO arrays in the United States, and then there's like three not quite as large detectors in Europe, and then there's one in Japan, and there's one coming online in China. So using more, we'll be able to locate much better locate an individual object that the gravitational waves are coming from. And then but that's generally the way they compensate on it. Usually a detection was only made when both detectors were online, and anything like a little earthquake or like an industrial, like if they're blowing up a building or something like that in a town 50 miles away, that can make a big difference. And because it has to be very precisely still by the time you start taking data for it to be accurate, because the noise is much larger than the data. You know, the external noise is much larger than the data. But redundancy, I would say, is how they look, you know, do dropouts.
Interesting. Yeah, I'm just thinking about how I might apply this to like all the life science microscopes. Because like the point of a lot of these microscopes is to get high resolution. So like data dropping, like they can't tolerate dropouts either. Yeah.
Well, and I know, and you may have run across this too. There are a lot of use cases where part of what you do for reduction is actually just removing chunks that are not useful. So like some of the microscopes are really taking a series of images that are make like a movie, a time resolved movie. And there's going to be chunks of times where like nothing's happening or you don't care as much. And so making critical decisions about removing that, I've seen experiments where like 90% of the data ends up being removed because it's really only what's happening in this 10% window, especially with all the like setup and, you know, the time that it can take for all that part. So I know there's some strategies for doing that real time, like the software that controls the microscope can show you and you can say, okay, just do this part. But there's even some that happens like somebody has to just sit and look later after the fact when they're not using precious microscope time.
Yeah. And that's the trick though, is how do you still get that terabytes of data to the person to sort through it? There's still that intermediate getting from the instrument to the analysis.
Yeah, I mean, we would have workflows for like cryo-EM and CT machines. We'd have workflows that, you know, like you said, the disk on the instrument, the instrument workstation, that disk space fills up pretty quickly. So we'd have enough on it to probably do three experiments, and then we'd buffer it onto I like a Synology array that was in the lab. And from there, we do some more, you know, probably do the data reduction there and then send it off from, you know, to the high performance, you know, computing arrays to actually do a lot of the processing on it. So, and we, for the CT machines, at least we just set up a Globus workflow when it would, when the image was finished being taken, it would fire off a Globus job right away and then get it to the other, you know, the workstations in the labs. And then it would also, and then we, once the, you know, somewhat minor data reduction was done there, we'd have a Globus, you know, workflow automatically move it to the workspace on the clusters. You know, and then we'd also have a way of moving it into archive that wouldn't make the people that run the archive crazy, because a lot of those, like I forget who was saying it, but a lot of the CT data is where you have a couple really large images and then you have tens of thousands of these really small TIFF files. And so we package those all up, make a manifest, and then we end up moving about 6 files to, including the manifest, to archive instead of moving 10,000 files, and not, you know, get the folks after us that run the archive. So
Yep. Brooke Palin at Michigan could talk your ear off about the math about this. And it's really funny now at Arizona, we don't talk about like the number of files at all. Mostly it just comes up and like, why is this so slow? It's like, it's because you have thousands of files, and that's the end of it. But like at Michigan, the way they charge for archive is space and inodes. So yeah. But it's an interesting calculation, and I don't know why it's not a thing in Arizona.
Just as another example, this does remind me. I've seen some, I guess, broader trends. Um, so as far as I guess reducing the amount of data, when we've been collecting data from some of our edge locations, we like 10 years ago, we used to pre-process that data and take what we called snapshots. So we actually had it was all through virtualization, but we had a essentially local computing cluster that would pre-process our data and take snapshots. And the idea was just to snapshot the data that we're concerned about, discard what we don't need, and then we transfer less data that way. Now, that stopped about 10 years ago because the big boom of cloud services, and all of a sudden everybody just stopped caring about how much data. They just get all the data. But now we're seeing a trend, and well, even broader speaking, I mean, I've seen more papers published, and there's even some startup companies now that are having more of a motivation from a sustainability standpoint and trying to reduce power consumption, but then also reduce their costs for like storing data and whatnot. So now we're kind of seeing this reemergence of what used to be our old strategy. Like, okay, now we're being asked again, okay, maybe we should go back to snapshotting our data and let's reduce that data again to, well, yeah, reduce power consumption, reduce cost. And like I said, I've even seen actually there's a few startup companies now that I've seen that are, well, especially like focused in the AI space, where they're claiming that we can use 90% less data and still produce a similar model, things like that.
Ooh, and that is a great segue into the next topic. Yeah, what to do with the death of unlimited cloud. Or, well, I think that was mostly a higher education thing, but it sounds like there's at least a similar problem over in the industrial for-profit space. But just talking about all this, like having to somehow package up files to archive them, all that. So kind of the biggest hurdle for like my microscope use case is all life science folks who are very desktop based and like point and click and don't understand the underlying parts of how computers work. So, but they're the ones who are using like the largest data files. And it's like how there's this big educational hurdle of like, sorry, you're making so much data that you can't have your nice like Dropbox, Google Drive interfaces anymore. And you can't just like shove things places and forget about them. You do have to do things like curate the data a bit beforehand and figure out how much you actually need to keep. Then you also need, like, there needs to be some manual tiering in there a lot, because I guess the way to put it is that storage tiering in research is event-based and not time-based, which is what I've had a lot of trouble getting enterprise IT folks to understand. So it's not like you can move this to tape after it's been untouched for 1 year. It's more like you can move this to tape after it's been published. Because there's definitely people, like I had data sets that, like the first data sets that I would finish for my paper, those would probably go untouched for like a year as I was getting other data sets. So it still needs to be somewhat close at hand, not on archive until I've used it, but it could be a very lengthy process. That's kind of, yeah, the piece that a lot of enterprise folks don't know about.
This is why in Starfish Land, we, especially when working with EDUs, we generally work with individuals in the group to say, okay, this project is done. You can move it somewhere else. And anytime that someone wants to impose some sort of time-based thing, that generally doesn't fly in higher ed, but in industry, we've seen some pretty incredible decisions that would not fly in higher ed. I'm working with this one big pharmaceutical company right now that's just going to take all their data that hasn't been touched in 3 years and send it to Glacier by file. So they've negotiated a better price with Glacier, not going to tar anything up. They're just going to take each of those files and fling each of them up there. But, they're going to provide each of the different groups a way to jump into a starfish zone and restore files as needed, and they're not worried about the cost to bring them back. So interesting range of problems and solutions for sure.
And I think you just touched on something that's kind of an assumption for we in higher ed, in terms of the getting the data back, right? So we have what do they call it? Egress waivers. Is that the right thing, Jan? So that we don't get charged for taking it out, but that's not true throughout. That's not the way these Amazon and Google and some of the others normally work, is you have to pay to get it out. So you can very easily, it's like a garbage can, or it's very easy to put stuff into it, but it's harder to get the right stuff out, and you have to pay for it. So you have to be somewhat organized in that world if you don't have that assumption of data ingress fee waivers.
Yeah, kind of like going back to my example, like if I'd put my first data set in Glacier, I'd have to pay quite a bit to get it back once I was ready to actually put it in my paper. And that's why, like, I usually think about storage in 3 tiers, and I've heard a couple of names for that middle tier. I've heard Nearline, I've heard Cool, but yeah, it's kind of like in the middle of active storage and things like Glacier. That's yet another tier for everyone to deal with and manage.
So wait, what do you mean the 3 tiers? Can you elaborate on that a little bit?
Sure. So there's the active tier where you're actually doing analysis. That's the performant and expensive stuff. There's an archive tier. Yeah, that's the glaciers and all the tape archives you might see as for data that doesn't need touching anymore. Nearline is kind of like somewhere in between. So it's not as performant as the active stuff. So you don't have to like pay for the expensive stuff for this data. You're not gonna need frequently. But it's also not an archive where you have to worry about like retrieval times and egress costs and all that. Yeah. I guess for higher ed, it depends on like how storage is set up at the institution, or more like how it's funded. But like I've seen most storage models are per terabyte. So it's just kind of like third tiering price to help with that, basically.
I'll add, I mean, I am not a storage expert by any stretch, but there are multiple strategies to reduce your storage costs. And, one of them that I'll mention is oftentimes researchers will set up their own AWS account independent from like a central cloud account, and because they can, right? They have their own funding, they've got their own needs. Maybe central IT just doesn't really understand their computing needs. But one of the benefits of having all of those research related accounts under a sort of one cloud account umbrella is that then everyone is contributing to the data sort of tally. These are obviously not technical terms, but when one wants to take that data out, that egress is not just your counting against your own data, it's part of the larger total. So we did an analysis early this year looking at egress costs at AWS and how often people were actually charged a fee. And it was fewer than 1% of all egress actually incurred a fee. And so I totally understand the anxiety of the concern of the unknown future egress charges one's research might incur. But I will say, in realizing real data over multiple years of use, I think it was over the past 5 years, it was a very tiny fraction of accounts that were actually charged. And those accounts were already very anomalous data users. So if you think you have a use case that falls into that bucket, talk to your account manager. They can definitely strategize with you. You're probably already very well acquainted with them and working closely with them, but I mentioned that just because yeah, there are savings to be had.
That's interesting data. Yeah. Kind of it's aggregate data though, and what I've seen with the way a lot of these accounts are set up at universities is like the individual researchers' usage is still passed through to them for the cost. So if they are in that 1%, they have to shoulder everything, which is what they're trying to avoid.
Mhm.
Yeah.
It's cost recovery. That's the word.
We've already discussed a variety of solutions that kind of go back to the research process and ask whether the research methods can be adjusted. Sometimes the computational method, sometimes the method of like with snapshotting, how much data actually needs to be saved if a simulation has like really high resolution to get the physics right, but how frequently do you need to see an image of that simulation to be able to do downstream analysis, that kind of stuff. But there's also, and I took notes on this, like, so cloud basically favors use cases where large data you might bring in and then it's reduced, where the computing that you're using the cloud for is data reduction, or where like large data is produced and then reduced and you don't need that large raw data. It really disfavors like a use case that's purely like, I'm creating a big data set just to create it and then I need to get it out. But going back even to the use cases that we've already mentioned, there are also approaches, and Jim's not going to be surprised that I'm saying this, where you can change the computational approach too. Like let's say the data is in a really large repository, not in the cloud, or it's in a place where your computing processes in the cloud can access it. In some cases, researchers are using a method that may be like tried and true, especially for smaller data sets, but now they have this larger data set that takes in all the data into one computer, basically, however you want to think of that, multi-core or whatever, one core, where they really could adjust their methods so that they're distributing this in a high throughput way, and where like each computing task only needs to grab a little bit of the data. And so you never have to bring a whole huge data set into any one computing unit. Instead, each of those computers can also then be distributing the access of just the portion of the data that they need to be analyzing. And then you can bring all the results together in the end. Of course, you have to have an origin for that data that is okay with being accessed at whatever frequency you need the computing to be happening at. But it's important, I think, that high throughput computing approaches apply not just to splitting up the computing to make it faster and parallelize it, but also to parallelizing data access.
Yeah, one thing I'll say is that this hybrid data storage solutions is becoming a frequently encountered I guess, situation now. Frequent enough that there's been, I guess, various technology platforms that have come out. They're known as HSMs, hierarchical storage management solutions. I haven't made a lot of use of it yet, but we're seeing more need to make use of that. We actually do have, it's through the company Calray with their Pixstore data platform. They have what's called the Ingenia HSM, which that would allow, in theory, to potentially use AWS Glacier, maybe even S3, along with the on-prem data that we host on what is ultimately it's an IBM GPFS file system, and that's where you can develop a strategy to potentially, if needed, you could unarchive some data from Glacier and use that. If you need to reference on-prem data, I mean, there's just various options like that. But like I said, there is various solutions out there now for, I guess, the hierarchical storage management space.
Well, we only have a few minutes left, and I believe this room's gonna be used for something else here in a bit. So thanks everyone for coming. This is a very good discussion. Glad you could make it. And we'll see you not next month. We're canceling for the PERT conference. We'll see you in August.
Thanks, everybody. And I'm just sticking around for the next thing that happens in this room, so.